And I'm going to give you a warning, folks. One thing I learned last week too is if you are recording with Zoom to your local machine and you establish a Global Protect VPN connection using Palo Alto's Global Protect, it will break your recording. It will stop recording and you will lose the recording. I do not know if that is also true with recording to the cloud, but I do know last week on Wednesday during my network security class, I was teaching and wanted to show a VPN connection. I connected, didn't see that it actually turned off the recording. Next thing I know, at the end of the class, there was no recording. So don't get caught out like I did. You have been warned. So learn from my mistakes. So let's talk a second about more wireless theory, basic wireless theory. So RF signals will decrease even if it travels through nothing but free space, so open air. And that's called free space path loss. So if there's no obstacles in the path, then the signal strength will lessen. It's also exponential. In other words, it has a huge drop right as it leaves the transmitter. But then as you get further from the transmitter, the free space loss becomes less or it drops off. So it's an exponential loss. One of the things I want you to be aware of is that I got some notes here, but a couple things, some concepts. The received signal strength indicator is how much signal is received on a device at the receiving end. You also need to remember signal to noise ratio, and that signal to noise ratio, you want your SNR to be high. Now, why is that? Why does that make sense? Well, it's signal to noise ratio. You want more signal, less noise. You want good signal so you can have a good connection and get your information. You want less noise. So signal to noise ratio, higher is better. We also need to talk again about this relative power reference in terms of decibels. If you say that a sending device has one level of decibel and there's a 0 dB loss, which would never really happen, be almost impossible to achieve. But if you were to say there was a 0 dB loss, that would mean the signal when it left the transmitter got to the receiver and had the same power level. So if it left at 10 milliwatts, it would get there at 10 milliwatts. Now, if somehow you had a 3 dB gain in the system, that means it is 2 times the power. So if it was a 10 milliwatt, it would be received at 20 milliwatt. If it's a minus 3D power, it's 1/2 the power. So it'd be sent at 10, it'd be received at 5. And then we got the 10 dB and the minus 10 dB. So 10 dB is 10 times the power, minus 10 dB is 1/10 the power. So just be aware, these are called relative power references, and it's used a great deal. And it's called the idea of 3s and 10s. So 3s is double the power or half the power. 10s is 10 times the power or 1/10 the power if it's a negative 10 dB. So just wanted to throw that out there. And so here's an example of EIRP. So it's actually the measure of how much energy is actually radiated from an antenna. So if you have a transmit of 10 dB, the antenna has a 6 dB gain, and then you have a cable loss of 3 dB, you would end up with a total of 13 dB. Now that doesn't relate to this 3s and 10s, but it's just showing you that how to figure out an actual emitted transfer power rate. And one of the things you need to realize is antennas typically give you gain and cables typically cause loss. So if you want to have a good signal, you typically try to make a shortest cable possible. So you wouldn't want 10 loops of cable to an antenna that's on top of your building. You'd want the cable to be the exact length needed to get to that cable with just a little bit to spare in case it needs to be moved. Does that make sense? We also need to talk about antennas and how antennas have different two different planes. One is an azimuth or H plane, which is looking down from the top, horizontal view, and an E plane, an elevation plane, which is looking at the side. And when you look at different antennas, they have different basically cells they build based upon the type of antenna. So omnidirectional antennas, depending upon what they are, you'll see on the elevation, the east side plane, it's a round, but looking down from the azimuth, from the top, it actually looks more like a little donut. And that can be determined by where you put the antenna. So when you look at your antenna, it is very important when you go to mount them on the wall that you understand the actual type of plane pattern that's going to be developed. Because if you put them one way, you could be, all of your energy could be going outside the building instead of, because you think about that, if you were to mount this on the wall and it was a donut and you mounted it correctly, the donut's going to go down into the building with the access point being here in the center. So here's an access point, it's in the center, and the donut will radiate out this way on one part of your hallway and then radiate out on the other side this way. But if you were to reverse this, it could mean the donut actually goes, let's say you put it in the front of a building, part of the donut could be out in your parking lot and the other part of the donut could be in your classroom. So it's very important you understand which way to mount the antenna to get the correct signal strength that you're looking for. Okay. You also need to understand directional antennas. One of the things you may get on the test is they may actually give you a picture of a view here and say, what type of antenna is this? Some of these are fairly easy because you can look here and see, okay, look, that looks like a directional antenna because it's mainly the energy is going in a single direction. Same thing with a Yagi or parabolic dish. Notice how the parabolic dish pretty much goes in a single direction. Yagi is the same. Look at, it's showing you the dB gain for these antennas. So a high gain single mount 5.2 dB. The Yagi is, this is 13 dBi and then a 21 dBi. So be aware that these are the types of things you'll see in the book and things you need to know for the exam. And also you need to know it when you're developing your wireless setup. I'll also tell you one of the things you've got to do in the real world is you've got to walk around with a device and actually test your building to see the types of connectivity you have and signal strength. The building I'm in right here behind me, the wall behind me, let me turn off my, change my camera a little bit. I'm gonna remove my background. So let's say no background. Okay. So now you can see behind me here, this wall back here, okay, it looks like a regular wall, but this building was built in two parts. So what actually is happening is behind this wall is an exterior wall. Then on the other side of that is another exterior wall that used to be the front of the building. So the back part of this building was about 12,000 square feet. The front part's about 12,000 square feet. They didn't have the money to build all the buildings. So they built the back 12,000. About 4 or 5 years later, they built the front 12,000. That meant they had to pair up two external walls together so that if you try to put a wireless access point in here and serve the other side, it's not going to work. Now, if you didn't actually know this building and you just made an assumption that that was a regular wall instead of testing, you would try to install X amount of access points and you'd come in and it wouldn't work. So make sure you do the testing along with the actual just looking at the walls and trying to figure out. Okay. Now I'll come back to this in just a second, but I want to show you again, going back to chapter 18. I'm gonna go back to chapter 18 real quick. Get chapter 18. So we were talking also 2 weeks ago about wireless infrastructure, and we were looking at the difference between lightweight access points and autonomous access points. Remember, an autonomous access point has full ability to be self-sufficient and can be standalone. In other words, it doesn't need a controller. It handles all the information inside of that access point itself. The problem with autonomous APs are that they can be expensive to maintain, and they're very hard to maintain when you start getting into the hundreds of APs that you find in large campus environments. So we have developed, and Cisco has developed, a different type of AP, which is called a lightweight AP. That AP still handles many of the functions that are what we call high-speed or split MAC architecture. In other words, things, the real-time processing functions, the joining into the AP, the ability to do MAC address information, hand off SSIDs, those types of things. All that's handled in the actual AP itself. But the AP forms a CAP/WAP tunnel back to the controller, and the controller handles things like software updates, VLAN information, all of those items that are a more intelligent and require more information. A lot of it's layer 3 information. All of that's handled by the wireless LAN controller. You can support up to 6,000 in large enterprises wireless LAN, wireless APs, autonomous APs per wireless LAN controller, depending on what type of wireless LAN controller you have. You also have the ability, and this is an interesting thing, and this could definitely be something you might see. You should have a round trip time between the AP and a controller of less than 100 milliseconds, so that real-time wireless can be handled in almost near time. If you have even less latency, it's better. But that makes it so that the controller and the access point can send information back and forth to one another. If it does not maintain that 100 millisecond or less, your access point may go looking for another wireless LAN controller that's closer to it to provide better functionality. Okay. Here's an example of an embedded wireless LAN controller where you can actually sometimes have a wireless LAN controller not only in a switch, but you can have it in another access point. So there can be an access point that has a wireless LAN controller in it, which allows you to have even faster connectivity. Now, you'll notice this CAP/WAP tunnel here. The importance of that CAP/WAP tunnel, and so they keep pushing it all the way down to, and this is that Mobility Express network topology, and this is actually having the wireless LAN controller itself is built into an AP. And then that produces CAP/WAP tunnels with the other APs across it. This is designed for small environments, so less than about 100 APs. So be aware of that as you start moving it further down, you have less functionality because these embedded devices cannot control as many access points. But the beauty of this is this: when you turn on a wireless access point, all it needs is an IP address. Once it has an IP address on it, it will go and discover it's a wireless LAN controller. And then once it discovers that wireless LAN controller, it can even be what they call touch-free. You do have to configure the switch port where the AP connects, make sure it's in the correct VLAN, the access and access mode, and power settings for PoE and those types of things. But when it boots up, it'll boot a small iOS image, and it will go through wireless LAN controller discovery. So it's going to attempt to build that CAP/WAP tunnel, and it's going to try to find a wireless LAN controller. And we'll talk about in a minute how it does that. Okay. But once it does, it's going to join the wireless LAN controller, download the full image of the software that you want that device to have. So in other words, cool thing is these lightweight access points, you don't have to manage the iOS on them. They're going to boot up with a small iOS image, get access to the wireless LAN controller, and then download whatever image you're using on all your other APs, and they'll be updated to the current image. Neat thing too is you can push updates out across the wireless LAN controllers. They will then download the configuration, whatever the config is from the wireless LAN controller. That's sent. Things like service SSIDs, quality of service parameters, all that. And then it will go into what's called the run state. And once in the run state, it starts providing basic service sets, so SSIDs to clients and allowing clients to connect. And then if for any reason there's a reset or the AP is turned off and on, or the wireless LAN controller for some reason is unreachable, it will actually tear down the CAP/WAP tunnel. You'll notice here one of the important items I mentioned is if for some reason you believe a wireless LAN controller or an AP may connect to a different wireless LAN controller, let's say you put in a new one, or you are, for whatever reason, you should have redundant wireless LAN controllers. You should always make sure your wireless LAN controllers are running the same code release. Otherwise, you could end up with a problem on your APs. You could end up with an incompatible code release on the wireless LAN controller paired to a an AP that has an image that will not work with that code release. Now, here is how this takes place. The AP creates a CAPWAP discovery over UDP to port 5246, and it's broadcast out on a local subnet. If there is a wireless controller there, it returns a CAPWAP discovery to the AP. And then when that happens, it gets the CAPWAP tunnel. Now, the cool thing is you can actually prime an AP with a primary, a secondary, and a tertiary wireless LAN controller. So those are stored in NVRAM. So basically, when you go into the AP and you set it up to be either DHCP or static, you can also prime it with up to 3 different controllers. If it's already joined a wireless LAN controller before, by the way, you reboot the wireless LAN controller, it will store up to 8 of 32 WLCs for it. But if there's absolutely nothing there, okay, you can even have it to where DHCP sends out a suggestion through DHCP option 43 of wireless LAN controller addresses. So if your AP has not been set with a static IP address, it has not been set with the primary, tertiary, or primary, secondary, or tertiary wireless LAN controller IP in its pre-configuration, and you just hook it in DHCP only, you have the option under DHCP to let it get an IP address. Then it will actually use DHCP to use option 43 to try to initiate the CAPWAP tunnel. If that doesn't work, so let's say there's no primary, secondary, tertiary, there's no DHCP 43 option, the next thing it's going to try to do is look for a DNS entry of Cisco CAPWAP controller.local domain. And if that's in your DNS entry, it will get the name and IP address of the wireless LAN controller it's supposed to use. If none of these work, this AP is going to reboot itself. So you either need to prime it with a primary, secondary, tertiary, set DHCP option 43, or set the DNS option. Otherwise, this will not work. It's just going to sit there and reboot and reboot and reboot and reboot. All right. If you also get in trouble, if for some reason you are doing this process and your router is not allowing UDP 5246 to pass, there's actually an IP helper address, just like for DHCP, that you can set up. You can tell your router to forward protocol UDP 5246 and then tell it the helper address, which is the IP address that you would put in for the wireless LAN controllers. And it's always suggested you put in at least a primary and secondary, so that the access point can access one of those two, and if one's down, it can find the other. But this process is so neat because with it, if it works, the AP boots up, finds that wireless LAN controller either by primary, secondary, tertiary, UDP option 43, or the DNS option. It will then develop its CAPWAP tunnel, pull down its iOS image or download its image, and then it will actually download config, load the BSSs, and boom, you got a fully running wireless LAN controller, up to date with the newest software, and you did very little work. Questions about that, about lightweight access points? Okay. Again, they're telling you the exact same thing again. Primary, secondary, otherwise, and it will show you those. It also, one of the things that will happen if there is a primary, secondary, and a tertiary, and the AP can actually find multiple different wireless LAN controllers, it will try to find the least loaded WAN controller during the discovery page. So if multiple wireless LAN controllers respond to a request from an AP, they also respond with their load. And the AP, if everything else is equal, will try its best to go with the one with the lowest load. Okay. This is the best approach, is always put a primary, secondary, and tertiary controller field in the APs when you first configure them. That way you know for a fact it's going to try to go to one of those three. But if that's not an option, then you do have the other two options, DHCP and DNS. You do have multiple modes here. One is local, and that is the default lightweight mode, which has one or more functioning basic service sets. Remember, a basic service set is just an SSID that services clients that connect to it. You can have a monitor mode, and that is one that does not transmit at all, but it acts like a sensor, and it can detect rogue access points, determine position of stations throughout with location-based services. One of the things we're going to learn, you're going to learn as you read through here, Cisco even has the ability to do location services with wireless to the point of, I mean, almost down to the meter specificity. So you can find out where a wireless device is within a meter or two, which is kind of crazy. The monitor can help do that. Flex Connect, and that lets it switch traffic between SSID and a VLAN. If the tunnel is down. So in other words, if a CAPWAP tunnel goes down, this device can actually become an endpoint for CAPWAP tunnel, a sniffer, and then also a rogue detector. So there's a couple of different modes. You also can have a bridge, a Flex Connect, and that's for Flex Bridge, which is for meshes, and then the SE Connect, which basically lets you run a specialized monitor to look at your wireless traffic. Normally it's in local mode 99% of the time. In the other modes, if you do operate one of the other modes, local modes, and the ability to actually provide connectivity for clients, they're in any of the other modes is disabled. Okay. So if it's in any other mode other than local mode, you cannot actually connect to it as a client. I'm not going to go back over the antennas. We talked a little bit about that, talking about H-plane, looking at it from the horizontal. Elevation plane is looking at it from side view. So H is top down, horizontal looking down. Elevation view is looking at it from the side. The bigger thing is know that antennas have a level of gain to them. And so an isotropic or a perfect sphere would be no gain, whereas omnidirectional is +4 gain, and a directional can be up to, we can be more than 4 gain, but 12 gain. So your beam width is how wide your antenna radiation is. Gives you an idea of how wide the beam is. And then your polarization is how the signal is oscillated, and how it is in terms of its signal to the receiver. So how the signal is expected to be received on the other end. So if you want to receive signal to be the same, you try to match the polarization on your devices. Let's see if I can find a couple. Here's a Yagi antenna. Notice they're showing you again directional antennas, trying to show you the antenna, the radiation. Here's a Yagi antenna. Okay. An egg-shaped pattern extends along the antenna's length. Here's a parabolic dish, which is usually used between buildings. So we need to know those discovery states. If you want to do well on the exam, you need to know that. You need to know how the steps take place: primary, secondary, tertiary. UDP 43, or DHCP 43. And then last but not least, the DNS entry, that CAPWAP DNS entry. Now, when I was looking through this on my items, one of the things I tried to look at this, and I tried to look at functionality for who terminates the CAPWAP tunnel, and typically the CAPWAP tunnel terminates at a controller, the main controller. We then also need to talk about, I believe this is actually, let me go back to my next chapter. Oops. Actually, look at this. So we're going to look at roaming and what happens when you roam between autonomous APs. First off, by the way, if you roam between autonomous APs, you've got to have the same SSID. Otherwise, you're not going to roam easily. You're going to roam, but you're going to disconnect from one and connect to the other. And so you can actually lose connectivity. But that's autonomous APs got to have the same SSID. When you're roaming between autonomous SSIDs, notice the association moves to the new AP. So basically moves from one to the other. Okay. So that's pretty simple. That's not a big thing. Notice if you do roam between multiple different or the same SSID but multiple APs, you're just going to connect to each one of those APs as you move. You need to have enough overlap in the cells that you don't end up in a position where you can't connect to any AP during this roaming. Okay. With wireless LAN controllers, it depends on how your wireless LANs are set up to handle it. Okay, so in most of them, they're bound to the wireless LAN controller through a cap-wap tunnel. So if you move from one to the other, you can actually roam to the next one. Okay, so if it's the same AP, same wireless LAN, they both have control of it, you can roam, all right, with what's called intra-controller roaming. And this is when you're roaming using the controller handling the roaming process rather than the APs because of split MAC. If both of them are involved, you'll see that it just moves across, it goes to the new client, and the wireless LAN controller moves it from one SSID on staff over to the other one, which is inter-controller roaming. It's not very different than just normal autonomous AP roaming. Okay. Now, the problem is with this, there may be a time when it's not fully associated with either one, and that can cause issues. Not necessarily a big deal, but it could be a problem. What we've got though is a little different thing. Is before an intercontroller roam here, we've got a client roams from one AP to another. They lie in two different controllers. The client makes what's called an intercontroller, not an intra. Notice this is an intra-controller. So if you're roaming within the same controller, it just moves it over to the next AP. Just like it was almost like autonomous APs, except that it's being handled by the wireless LAN controller. But if you're doing inter-controller roam, all right, and it is two separate controllers and the cap-wap tunnel is controlled by the they're connected to two different wireless LAN controllers. You'll notice it's going to either try to use the same IP address or work with DHCP server to get a new address. Here we see it roaming across from 100 to 100, so there's no change in the IP address, but it's simply when it roams between two different controllers, the association moves from one controller to the other controller. So it roamed between APs, but it stayed within the same VLAN. It makes a layer 2 inter-controller roam. Now in a minute, we're going to actually roam between two different subnets and things change, right? To this point, pretty simple. But let's imagine this is what we have. Let's imagine we initiate a roam, but there are two controllers involved and two different VLANs. In other words, the SSID is the same, but the VLAN on the other side is different. So what has to happen here is you have an intercontroller roam, but an extra tunnel gets built between the anchor controller and the wireless LAN controller you roamed into, so that that client does not have to receive a new IP address. It stays anchored to that 100 VLAN through a new cap-wap tunnel that is initiated between wireless LAN controller 1 and wireless LAN controller 2. So this is called an inter-controller roam between VLANs. And you'll notice that new tunnel. If we didn't do this, the client would have to drop its connection, drop its IP address, do a new DHCP, get a new IP address, do a new associate, all that would have to take place, and you would lose connectivity. That's not a problem up here in an inter-controller roam on the same VLAN. Not a big issue because you just move over, you're in the same VLAN, you just re-anchor to the wireless LAN controller that you end up in the SSID for. But if it's an intercontroller roam to a different subnet, you have to create a CAPWAP tunnel back to the anchor controller. And then the roam, the controller it's going through back to the anchor one is called the foreign controller. So you've got a roamed client on a foreign controller going back to the anchored controller. But with this, you can move between really anywhere. You can move anywhere and keep your original connectivity back to the wireless LAN controller you were anchored to. Now, there's all types of ways to set this up. And one of them is a thing called mobility groups. And if you create mobility groups, it allows you to roam between wireless LAN controllers. So this allows inter-controller roaming to take place. Their centralized controllers can belong to the same mobility group. You can have a large mobility domain, and then inside of that, these mobility groups, and then each client in the mobility group can move between these wireless LAN controllers without ever having to reinitiate the full connection. If you move between mobility groups, though, you're probably going to have to redo your connectivity. Okay. Now, there's actually a way to set it up to where even with mobility groups, you can have connectivity back to your anchored controller. Okay, so you have multiple groups and you're going to anchor between those. The issue there is typically there's a lot of setup involved. And so our mobility groups, we want to stay, we're going to design them so that our users, when they roam, they're going to roam within a mobility group. That's where they're going to stay most of the time. If they go between mobility groups, we typically just have them reconnect and get a new IP address, join a new mobility group. All of this is good because we can actually set up a way to do what's called location services. Anybody think of a use for location services? Other than the government tracking, not necessarily a good use. Can you think of a use for location service? Well, here's one that's been discussed that's kind of a little bit dystopian. If you've ever watched any science fiction, you can kind of think about this. Let's see if somebody put something in chat. Warehousing. Warehousing is definitely one. Yeah. That's possibly, you could use location to have wireless connectivity, track inventory with RFID. Yep, tracking mileage. That's a good one, Tamara. One of the ones that's also been suggested is to feed you special ads depending on where you are in a shopping mall. Let's say they track you, you've connected to the Wi-Fi in the shopping mall. They can give you an ad for one of the stores you're walking up on. One of the dystopian uses, if you've ever watched, oh God, what's the name of that show? It's on Netflix, and I loved it. I loved the first season. The second season wasn't. Altered Carbon. Have you ever seen Altered Carbon? In Altered Carbon, as people walked around, the ads that they were shown were given directly to them based on things they liked and who they were. And that's one of the location devices or location ideas. But you can even do real-time track data. If you want to have the ability to locate a device, you really need to get good location. You need at least 3 access points. So it's very difficult with a single access point, but with 3, you can start to triangulate based upon signal strength, and that can tell you about where the client is located. You can even then get into what's called Cisco's DNA spaces, to where you can feed in a map of a building and then tell it where the access points are, and then using that and the data from the connection of the client and its signal strength to certain access points that you may put in, let's say as a instead of having it in the local mode, having it in a monitor mode, and then those monitor mode devices can tell you how far or the signal strength to them, and that will let you figure out where a device is in your environment. RFID tags, there's a great, exactly one of those things that's set up. You know, I've always said one of the things, and they've kind of got air tags now, and we've seen this, but I always said that sooner or later we'd have where we could just stick a tag on our devices, and if anybody takes them out of our house, we immediately know they've been removed from the house, and we can start tracking them. That roaming or that location is something it's mentioned in the curriculum and in the test. But the big thing here is looking at how this DNA spaces allows you to do real-time location data. You can even look in, the idea is you can look on the map and find exactly where someone's at, or exactly where a box of widgets are in the warehouse. That's another idea behind it. So there's RFID tags. They only wake up on occasion. They're not meant to be awake all the time, because otherwise you'd have to have a huge magnet on them or a huge battery on them. But we can do this with our location services. So let's go back over this again about the movement between different items. So let's look first in autonomous AP. You're just going to move over and associate with the new AP. If you do intra-controller roaming, okay, you'll notice it just creates a new CAPWAP tunnel, or just creates CAPWAP tunnel back to the same controller. You'll be associated with the new AP. Okay. So it just knows which CAPWAP tunnel to use to reach that client. It just updates its tunnel because, or its information, because it knows that. It basically says this MAC address is available via this CAPWAP tunnel. So it's very, very important. But now if it's between controllers, as long as it's inter-controller roaming with the same VLAN, it just moves over, builds a new CAPWAP tunnel, and figures out who it's associated with. So what wireless LAN controller it's associated with. So it's not going to be a big issue there. If it's inter-controller roaming, but to a different, this is called, by the way, an inter-controller roam to the same VLAN. It's called a layer 2 roam. If you go to a different VLAN or a different subnet, it's called a layer 3 roam. And when that happens, you have to build a new CAPWAP tunnel back to the anchor controller. You need to know this. You need to know that concept right there and how that works, because you may get some roaming questions. All right. I had a good question about one of the labs. I will tell you too, our NetLabs folks, I shared our NetLabs with a group out of California because their NetLabs went down. And so you may notice if you try to do a lab reservation for our CCNA pods, you may actually see here for just a little while, you may see the first couple pods, first 4 to 8 pods are being used a great deal. It's because we're sharing it with a bunch of schools in California until they can get their NetLabs back up. But for us, one of the things I want you to be aware of is down here in this, our actual labs on SDN. Don't get confused, and one of your classmates did. Don't get confused by the command that asks you to import NetMiko. He thought maybe that you would have to have internet access. You're not importing the NetMiko package. You're simply importing NetMiko functions into Python, into the idle. And then you're going to create the script that lets you connect to the device and pull information off that device. So don't get confused by that. Just be aware that's all you're really doing is connecting so that you can see information and pull information using a Python script in NetMiko off of the device. And you can even make changes to the device, creating a loopback on the device using NetMiko and Python. Okay. Don't get confused by that. Other questions about our class, about this section on wireless? Know all, see all, hear all? Just ready for the semester to be over?
I've got a question about one of the labs, but we don't have to do it on recording.
Okay, all right. I'll turn off recording here in just a minute. Let me go ahead and turn it off.